You know, when you really stop and look at human history, there is this massive glaring paradox just sitting there in the timeline. And honestly, once you see it, you cannot unsee it.
Oh yeah, it is impossible to ignore once you notice it.
Right. Like we look back at ancient civilizations and we are completely in awe of their engineering. You look at, Stonehenge, the Roman aqueducts, Göbekli Tepe, and of course the pyramids.
Sure, the classic examples.
Yeah, and these are structures that still baffle modern engineers today. The level of undeniable world-class genius is just right there in the stone. So, I mean, if they were so brilliant, why did they never build a skyscraper?
It really is, well, it's the ultimate architectural mystery, I think. Because we tend to have this perception of human progress as this steady upward climb, literally and figuratively.
Yeah, like a freight line up.
Exactly. But when you dive into the actual data of how high humanity could build, that progress completely flatlined for millennia.
And to figure out why. Today, we are taking a deep dive into an incredible stack of sources. We've got architectural history papers, engineering journals, metallurgical timelines.
A lot of really dense material.
So much dense material. But our mission is to prove that this ancient absence of skyscrapers wasn't, a lack of intelligence. I mean, the Egyptians and the Romans were definitely not lacking in brain power.
No, not at all. What they lacked were specific mechanical and material milestones. And we're going to break down the 6 essential technological revolutions that humanity had to achieve before we could finally touch the sky.
Yeah, but before we even get to those revolutions, we have to talk about the timeline, because the scale of this stagnation is just hard to wrap your head around.
It is staggering. According to our historical sources, the Great Pyramid of Giza was the tallest man-made structure in the world, and it held that title not for a century, not for a millennium, but for more than 3,800 years.
Over 3,800 years? That is insane.
Right. Humanity's absolute peak of height barely moved an inch until the Lincoln Cathedral was built in the year 1311. So for 4 millennia, the pinnacle of human achievement was basically frozen in time.
And you contrast that frozen timeline with today's standard, right? Currently, the world's tallest building is the Burj Khalifa. It stands at a massive 828 meters tall.
Which is more than 5 times the height of the Great Pyramid, by the way.
5 times the height. And the Burj Khalifa has held that world record for just 17 consecutive years. I mean, compared to 3,800 years, that is barely a blink of an eye.
It really is. And it makes you wonder what was physically holding the ancients back for so long. So let's start breaking down these revolutions.
Let's do it.
The first barrier is just the brutal physical reality of the materials the ancients had on hand. Because to build tall, the very first thing you have to do is beat gravity.
And gravity is relentless.
Completely relentless. Ancient builders worked primarily with stone and brick, right? And those materials rely heavily on compressive strength, which means their ability to withstand being squeezed or crushed by a downward load.
And they were absolute masters of compression. I mean, you can stack thousands of tons of stone on top of a base layer, and that base layer isn't going to crush under the downward force.
Right, it holds up perfectly.
But reading through the engineering journals, you realize that gravity isn't just pushing straight down. As a structure gets taller, it experiences shearing and pulling forces.
Yes, and that brings us to the catastrophic flaw of stone, which is tension. Stone is incredibly brittle under tensile stress.
So it can't handle being pulled.
Exactly. It simply cannot resist being pulled apart or stretched. If a tall stone structure starts to experience uneven forces, it can't flex at all. It just shears and fractures.
Okay, let's unpack this with an analogy. It is like trying to build a tower out of standard wooden building blocks. You can put a heavy weight right on top of that stack and the blocks won't crush. But the second a lateral force pushes them from the side, they just slide and snap and collapse because they have zero flexibility.
That is a great way to picture it. Whereas steel, on the other hand, is more like a flexible, interconnected wireframe. It can bend and stretch under tension and then pull itself back into its original shape.
And that is the crucial difference right there.
It is. Because stone fails under tension, the only way the ancients could build something incredibly high was to make it incredibly wide at the bottom.
Hence the pyramids.
Exactly. A pyramid is shaped that way out of pure structural necessity. It utilizes a massive base and sheer mass because that was the only path to height that the compressive strength of stone allowed.
Which means humanity needed a revolution in metallurgy to break out of that pyramid shape. And that brings us to the first of our 6 missing technological revolutions, which is the load-bearing structural steel skeleton.
And this is a shockingly recent invention. The metallurgical timelines in our sources point to the late 19th century.
Wow, that recent.
Yet, the very first building that historians generally consider a true skyscraper is the home insurance building in Chicago, built in 1885.
Okay.
And what made it revolutionary was that it didn't rely on thick, heavy stone wall to hold itself up. It utilized an interconnected internal framework of steel columns and beams.
Which is wild because ancient civilizations were absolute wizards at quarrying and moving massive stones, but they just had no metallurgical process capable of superheating iron and removing the impurities to create structural steel.
Right, they didn't have the ovens for it, essentially.
Yeah.
And without that internal tensile skeleton, a vertical skyscraper is physically impossible.
Okay, so you develop the steel skeleton, you have finally conquered gravity, and you can build straight up.
Yes.
But the moment you do, you hit an invisible wall, right? As you push higher into the atmosphere, gravity stops being your primary enemy, and the atmosphere itself becomes hostile.
You essentially build a giant sail.
Oh, wow. Yeah, a giant sail.
Precisely. Past a certain height, the dominant force trying to destroy your building is wind load. Up in the higher altitudes, wind speeds are dramatically faster and more turbulent than at ground level.
And ancient civilizations had absolutely no concept of aerodynamic load calculation because they never built high enough or slender enough to even need it.
Exactly.
But, I was reading through the architectural journal in our sources, and they mention something called wind vortices. And I immediately thought of the pyramids sitting in the desert wind for nearly 4,000 years, taking the brunt of massive sandstorms. Did they just survive because they are essentially aerodynamic mountains?
The mass and shape are exactly what saved them. A pyramid is completely solid and incredibly heavy, and its sloping sides naturally deflect the wind. The air just rides up and over the structure.
Like a ramp.
Right, like a ramp. But a skyscraper is a slender, vertical object. When a high-speed wind hits a flat, vertical surface high in the air, it doesn't just push against it evenly.
What does it do?
Well, it creates alternating low-pressure zones that peel off the sides of the building.
Oh, so these are the vortices, like invisible whirlpools of air tearing at the structure.
Yes, they peel off alternating sides, creating a rhythmic pushing and pulling effect known as vortex shedding.
Vortex shedding? That sounds terrifying.
It is. If a slender tower isn't specifically engineered to disrupt those vortices, the rhythmic swaying will build up until the wind literally tears the building apart through structural fatigue.
So this is our second revolution, wind engineering. And the Burj Khalifa is a perfect example of this in action, right? Because it doesn't look like a pyramid, but it is surviving way up there at 828 meters.
Oh, absolutely. If you look at the floor plan of the Burj Khalifa, it has a very distinct tapering Y-shaped footprint.
Yeah, I've seen pictures. It looks like a three-leaf clover almost.
Exactly. And that complex tiered shape isn't just an architect trying to make it look futuristic. It exists specifically to confuse the wind.
Confuse the wind.
Yeah, as the wind hits all those irregular step surfaces, the vortices can't organize themselves into a rhythmic pattern. The aerodynamic design breaks up the wind load before it can compound.
That is genius.
It really is. And this level of highly complex mathematical fluid dynamics simply did not exist in antiquity.
Okay, let's play out a hypothetical scenario based on everything we have covered so far. Let's say the Romans or the Egyptians somehow invent the Bessemer process and get structural steel.
Okay.
And let's say they somehow magically understand advanced wind engineering. They build an 800-meter tall tower out of steel and stone. They have beaten gravity and they have beaten the wind. It is standing there, completely stable.
They would still have a catastrophic problem. The building would be completely useless.
The livability problem.
Exactly.
Because an 800-meter tower means you have to navigate something like 160 plus stories. Here's where it gets really interesting to think about. Imagine the ancient equivalent of carrying your groceries, or just commuting to work, up 160 flights of stone stairs in the Egyptian heat.
It is a brutal logistical nightmare.
Right. No one is going to live or work on the 140th floor if it takes them 3 hours of grueling physical labor just to get to their desk.
Which is why the third technological revolution, the safety elevator, invented by Elisha Otis in 1852, is the milestone that actually made height viable.
It's funny, think about the last time you were in an elevator. You probably didn't think twice about the fact that you were standing inside a suspended metal box hundreds of feet in the air, hanging by a single cable.
Most people don't. And we only trust that because of what Otis invented. Hoists and ropes and pulley systems had existed for thousands of years.
Like on ships and construction sites.
Right, but they were incredibly dangerous. If the hoisting rope snapped, whatever was on the platform plummeted to the ground.
Yeah, game over.
Exactly. What Elisha Otis invented was a safety mechanism. He attached a spring-loaded ratcheting system to the elevator car.
Oh, so it's automatic.
Yes, if the cable tension failed and the rope snapped, the springs instantly forced heavy metal dogs to engage and lock into the guide rails on the sides of the elevator shaft.
So stopping the car dead in its tracks.
Exactly.
That is the difference between an inaccessible monument and a habitable machine. Because without the safety elevator, a tall structure is just an empty vertical cave.
But even with an elevator, you are really just getting started on the machine aspect of it.
Oh, for sure.
A modern skyscraper is basically an enclosed vertical city. And cities need infrastructure. This brings us to the remaining technological revolutions on our list, which are advanced plumbing, deep foundation soil mechanics, and electrification.
Let's talk about the plumbing first, because the physics of moving water upward blew my mind when I was going through these sources.
It is a monumental challenge, honestly. Water is incredibly heavy. If you want to get a glass of tap water to a bathroom on the 160th floor, you can't just push it up a single 800-meter vertical pipe.
Right, because the water pressure at the bottom of an 800-meter pipe would be so immense it would blow the plumbing right out of the walls.
Exactly. The pressure would be catastrophic. Modern tall buildings have to rely on staged mechanical pumping systems.
How does that work?
Well, you pump the water up to a holding tank on, say, the 30th floor. Then another mechanical pump pushes it to a tank on the 60th floor, creating these distinct pressure zones all the way up the building.
Wow.
And then, of course, you need active, heavily engineered sewage systems to bring waste safely back down without gravity just tearing the pipes apart.
Yeah, the ancients definitely couldn't mechanically pump water into the sky, and they certainly didn't have the soil mechanics to support these structures, which is our fifth revolution, right?
Deep foundation soil mechanics, yes.
Yeah.
A building as heavy and tall as a modern skyscraper exerts just an unimaginable amount of concentrated point load pressure on the ground below it.
It is like a massive stiletto heel pressing into the earth.
That is a perfect analogy. If you just build it on the surface dirt, it will punch right through the crust, sink, or just tip right over.
And the sources explain that you have to understand the microscopic mechanics of the soil, the depth of the bedrock, and even the water table.
Yes, you have to engineer foundation plows, which are massive columns of concrete and steel, and they are driven incredibly deep into the earth.
Like pinning it to the ground.
Right. Sometimes they go all the way down to sit directly on solid bedrock. But the bedrock is too deep. Engineers rely on something called skin friction.
Skin friction?
Yeah, it is where the sheer friction of the soil, tightly gripping the sides of hundreds of deeply buried concrete piles, provides enough resistance to hold the entire building up.
That is wild. That dirt friction holds up a skyscraper.
It really is.
And finally, our sixth revolution, electrification. Because without continuous electricity, a skyscraper is essentially a dark, suffocating oven.
Oh, absolutely.
Yeah.
A building that wide and tall would be pitch black in the center without artificial lighting. Furthermore, a glass and steel tower baking in the sun creates a massive greenhouse effect.
Oh, yeah, it would be miserable.
Without continuous, massive electrical climate control systems pumping chilled air through the structure, it would literally be unsurvivable.
Okay, so let's step back and look at the whole picture. We have our six missing revolutions. We've got structural steel, wind engineering, the safety elevator, advanced plumbing, deep foundation soil mechanics, and electrification.
That is the list.
We have spent this time breaking down how the ancients were physically prevented from doing it. But the architectural history sources also touch on something just as fascinating, which is the why. Did ancient civilizations even have a reason to want a skyscraper in the first place?
And that question really highlights how fundamentally different their world was from ours. Ancient height served a completely different purpose than modern height.
Yeah, because when you look at the pyramids or the grand cathedrals, they weren't building office space.
No, they were building monuments, temples, and tombs. They were designed for one overarching purpose, and that is permanence. They were built to last for eternity.
And the way you achieve eternal permanence with ancient materials is through sheer, undeniable mass.
Exactly. You build a solid mountain of stone that the elements cannot easily wash away.
Yeah.
They were not trying to create usable, habitable floor space.
Right. They didn't need a corner office with a panoramic view of the Nile. They needed a structure that would survive for millennia.
The very concept of a tall, hollow building densely packed with offices and apartments is a strictly modern solution to a strictly modern problem.
And that problem is the extreme cost of urban land. Economics. It always comes back to real estate economics, doesn't it?
Always. In modern metropolitan hubs like Chicago or New York or Dubai, land is finite and incredibly expensive. If you want to maximize your financial investment on a tiny plot of land, the only direction you can go is up.
You have to invent real estate out of thin air, literally.
Right, but ancient cities simply did not face that specific economic and spatial pressure. If an ancient city like Rome or Uruk needed to expand to house more people, they just built further out. They had the horizontal space to expand.
So, what does this all mean? It is a collision of necessity and technology. The ancients didn't have the technology to build up, but they also didn't have the economic necessity to even try. It really reframes how we look at their achievements, doesn't it?
It does. It is so easy for us to look at the lack of ancient skyscrapers and assume it represents a lack of ambition or a lack of know-how.
Right, like we are just inherently smarter now.
Exactly. But as the engineering journals make clear, ancient builders were every bit as genius as today's structural engineers. They solved massive logistical and physical problems that still stump modern experts today.
They were basically playing the game of engineering on the absolute hardest difficulty setting, but with a completely different set of tools. They weren't limited by their minds, they were only limited by the calendar. They were just waiting for steel, for elevators, for electricity.
When you compare the Great Pyramid to the Burj Khalifa, you aren't comparing a primitive structure to an advanced one. You are comparing two absolute masterpieces that represent the ultimate expression of the tools, the materials, and the societal needs of their respective times.
I love that perspective. It is not a competition between the ancients and us. It is just a showcase of human ingenuity adapting to whatever materials are at hand, whether that is limestone or structural steel.
Exactly.
So we started this deep dive by looking at that staggering 800-year reign of the Great Pyramid, and I think we have proven that the absence of ancient skyscrapers was really just a matter of mechanical milestones.
We have. But looking at the fundamental differences between these two approaches to height the ancient mountain of stone versus the modern vertical city, it leaves us with a fascinating and perhaps slightly unsettling final thought to consider regarding the nature of what we actually build today.
Oh, I'm intrigued. What are we left with?
Well, as we established, the pyramids were built as solid mountains of stone, designed specifically for internal permanence. They require absolutely nothing to survive.
They just sit there, enduring the centuries.
Right. Our modern skyscrapers, on the other hand, are highly complex, hollow, delicate machines. They're completely reliant on active, continuous utilities like electricity, water pumping, climate control, just to survive and remain habitable.
They need a constant heartbeat of power flowing through their veins.
Exactly. So the question becomes, if all human civilization stopped tomorrow, if the power grids went down permanently and the mechanical water pumps seized up, will the Burj Khalifa last 800 years in the desert wind like the Great Pyramid did?
Oh, wow.
Or has our modern quest for urban efficiency and towering height made our greatest architectural achievements uniquely fragile?
That is wild to think about.
Yep.
We built the tallest structures in human history, but we had to build them out of glass, wire, and continuous energy. Going from an eternal, self-sustaining mountain of stone to a beautiful, highly fragile machine.
It is quite the shift.
It really is. That is definitely something for you to ponder the next time you are standing at the bottom of a skyscraper, looking up into the sky.